Hey friends, welcome to another video on UNET implementation. In this video, we are going to replace UNET encoder with the pre-trained VGG architecture. So let's start the code. We start by importing all the layers which we need. Let's start. So we need like convolution, batch normalization, activation mix, max pool, transpose convolution, concatenation, and the input layer from the TensorFlow.keras.layers. So let me paste all these things. Okay. So next we need the model class from the TensorFlow.keras.models, because as we are using a pre-trained VGG16, so we need to import the VGG16 network also. Let's import that. Import VGG. Okay, should be capital. Now we have imported the VGG16. In the next you will see more pre-trained architecture used with UNET. So this is going to be just a starting, and there are more videos about it. We're going to cover VGG19, ResNet 50. We're going to cover DenseNet. Okay, the NestNet maybe. NestNet is really large. You can see. We can do that also. Okay. So let's start by building some basic layer. Like let's build a convolution block. So a unit consists of two 3x3 convolution layer, and each followed by a activation. But with the introduction of batch normalization, we insert batch normalization in between the convolution and the activation layer. But in the original unit, there is no batch normalization. So let's first build a basic convolution block. Inputs and then a number of filters. So I already have a video on the unit implementation, the original implementation of the unit. You can click on that I button or check the description for that video. And you can also check the code. It's on my GitHub. I will provide the link for that also. Okay, now let's continue with that code. Convolution layer. Then first of all, we need to provide number of filters. Kernel size is 3 and padding going to remain the same. Okay, so we'll give inputs as the input to this convolution layer. Next is batch normalization layer. And next we're going to start with the Relu activation function. Relu is one of the most simple activation function. It is very fast. It's not that computationally expensive if you compare it with the sigmoid or 10h. Okay, so first layer, first a few layers are ready. So we have convolution, batch normalization, and then Relu. So we're going to repeat these layers again. So we're going to copy them and paste them again. Then we're going to change the input for second convolution layer. So now we will return x here, the output of the activation, Relu activation function. Okay, now this is ready. Let's start by building the VGG16 UNET function. Build VGG16 UNET. Okay, so we're going to give it an argument input shape. It's like 256 by 256 by 3, or you can say like 128 by 128 by 1, what you want. Okay, it's up to you, it's your choice. So let's create an input layer. We have already imported the input class. See here we have this input class, and we're going to use this input class, and we already have the input shape. We're going to provide it input shape. So we have our input layer ready. Now in the original unit we are followed by encoder from scratch, but here we're going to use the pre-trained VGG16 model. So we're going to import some of the layers from it. We're going to remove the bottom classification layers. So first of all, let's build the VGG16 model and get the weights. So we no need to include the top, we just need the basic model. We don't want the classifier attached to the bottom, so we're going to set include top false. Weights, we want weight from the ImageNet. Okay, so ImageNet basically refer to the data set on which it is trained, and input for this network is going to be input tensor equals to inputs. which were specified above. So we have this VGG network ready. Let me print it summary. So we can see the whole lot of layers what this architecture has. Let us call this function. So input shape, let's define it here. Let's say, sorry, say 512 by 512 by 3. Okay. Now we'll call this build VGG16 provided input shape as the argument. Okay, it should be input shape. Okay, now we're gonna run this model. So let's run it and see for any error. Okay, it should not be layers, it should be applications. Okay, that's my error. Applications should not be layers. Okay, now let's run it again and see. Okay, so you can see we have got this summary. So it contained total about, I think, 14 lakh, not 14 lakh, 1 crore 47 lakh 140688 parameter. So the input shape is 512 by 512 by 3, and subsequently it decreases the resolution and increases the number of filters. So at last we can see we have a resolution of 16 by 16 by 512. So we're gonna use this entire architecture. You can see at the bottom there's no classifier layer, or you can say that no dense layer is there, no linear layer is there. So we're gonna take this model. This is because we have set include top is equals to false. Let's say if we set it to true, what would happen? Let's see what would happen and what changes would occur. Would we get some error, or what do we get? We'll see. Okay, I'm not. Okay, there's some issue with the GPU. With GPU, my memory is low. Let's say like 128 to 128. Run it again and see. Okay, it's downloading the wait file for that. Let's wait for it. Okay, so 5 seconds are remaining. 3 2 1, and okay, the weights are downloaded. And now we have another issue, this shape compatibility. So I think we need to specify some more things. Okay, there's some issue while loading the file. Do one things. Okay, let's for now we should 224 to 220. I think that can also be, this input shape can also be an issue. So let's hope this time we get something good. Okay, so you can see this time we have something good. These issues are because of shape compatibility. We also need to check the shape also. Okay, so you can see the input shape is 224 by 224, and this time we have got the classifier or the dense layer. You can see in the if we said include top to false, we would get features till here, till block 5 underscore pool. But if we said include top to true, then it would add these classifier layer automatically. So these are few dense layer and they contain a lot of parameter, but we don't need them. So that's why we would set include top to false. Include top to false. Okay, and we're going to change back to 512. Okay, let's print it, and now we need to extract some layers from it. Let's imagine this is the input and this is the output of the encoder. Okay, so we need to extract the skip connection from these, like we get in the unit. So if we have input size 512, so first skip connection size would be of 512. So this is the last size with 512. So this is going to be first skip connection here. So this feature is going to use as first skip connection. So like these, we're gonna have to for 256 by 256. So here we can see block 2 underscore con 2 would act as second skip connection. So now you're gonna ask how we have to find these skip connection. So these skip connection are basically some features from the encoders only. So in case of unit, these are basically output of the Relu activation function. So we're gonna check the size, what size of feature what size of skip connection we need. So first of all, we need a skip connection size 512 by 512. In this summary, we can see the last feature with the 512 by 512 resolution is this, the block 1 underscore convolution 2. Okay, so we need this name specifically, and we need to then we extract the skip connection. Let's say encoder here. Okay, s1 is equals to name of the architecture, like VG16. Here we have defined this variable VG16. We're gonna get a dot get layer, and we're going to write the name of the layer, and we can say output. Okay, now we're going to print its shape for further confirmation. Okay, you can see we have 512 by 512 by 64. So like this, we need to extract further skip connection of other shapes. Let's say this is 512. So next we need 256. So we're going to copy this, because only the block layer name and the variable name should be changed. So now here we need 256. Let's write here 256. So let's check for 256. So this is the last feature map with the resolution 256. So this same procedure go with the VGG16 ResNet 50 and all the other pre-trained networks. So UNET has 4 encoder blocks. So we're going to extract 4 skip connections. And here we will write 128. Okay, let's do another S4, and output would be 64. Okay, so now we have to do it for 128. Okay, for 128 it's block 3 con 3. Now for the 64 by 64, and it is block 4 con 3. It's not copying correctly. Okay, done. Okay, we have done with the encoder. Now there's a bridge part also. Okay, so we have to do that for bridge also, because after that it's followed by the bridge. After encoder we have the bridge, or the bottleneck part of the unit. So we're gonna get the bridge also from the this VGG16. So we're gonna say VGG16 again dot get layer, the name of the layer, and then output. And bridge will be like 32. Okay, so we're gonna see the size for 32, and it's this block 5 con 3. Okay, we're gonna paste it here. Okay, that's correct. Now we move on to the decoder part. So in encoder you can see how we have used this pre-trained VGG16, which is trained on the ImageNet dataset, and we have used it as a pre-trained encoder. Pre-trained encoder, as basically they contain weights which are already fine-tuned for some ImageNet task. So we're going to take advantage of them while training. Okay, so these help in early convergence, because these weights need not to be much trained. Or you can either do something, you can freeze some layers and then train it and then check how it works. It would be different for different data, but if your data images are same as more near to ImageNet, the more benefit you get. If the domain is much entirely different, so you will not get much benefit. Maybe you get benefit, but not that much if the domain would be nearly same. Okay, because ImageNet is on natural images, so if you're doing segmentation on natural images, it would be much better. So now we will start building the decoder block. So decoder block is basically first the input, then skip connections, and then number of features. Okay, it's basically inputs, skip connections, or we can say skip features, and number of filters. Okay, so first of all we are going to use a transpose convolution layer, or conv2d transpose. Here we're going to upsample a feature map by 2. So if the size is 32, we're going to increase it to 64 by 664. number of filters, and kernel of 2 by 2. So the original unit uses a transpose convolution with the 2 by 2 kernel. Right is equals to 2 because we want to double the number of the height and width, the resolution. Padding is going to be same, and input is going to be inputs. Okay, now we're going to concatenate the upsampled feature map and the skip connection feature maps. Concatenate. Okay, x the output for the on 2D transpose and the skip features. So make sure that the resolution of the x and the skip features are same. So you can see here we're going to give input as b1. So b1 is 32 by 32, and it's going to increase to 64 by 64. So output here would be 64. Okay, so skip connection is also, so this s4 is going to be skip connection for the first decoder block. So the both are 64. That's why they can concatenate. Let me just do one thing. Just write the code here, and we will see the shape practically. So the b1 and skip connection will be s4 and 512 the number of features channel. We're gonna see shape, print x dot shape, and the skip features dot shape. Okay, so we're gonna run it and check. Okay, so you can see the resolution is 64 by 64, and here again we have 64 by 64. So both the features have same resolution, so always make sure that you have same resolution. So if there is a difference of like one is 63, one is 64, so you can pad them with 0. Okay, but make sure that they are same. If like one is 64, another is 32, then I won't recommend you to just pad zeros, because there is a lot of unnecessary information, like unnecessary zeros would be there, so that would not be much helpful. So make sure that you take accurate skip connection. After concatenation, we're going to add a convolution block. Okay, so now we're going to return the x, the output of the convolution block. Now we're going to add 4 decoder block like this. So variable would be d2, and the input would be d1 here. The input for the second decoder block would be the output of the first decoder block, and for the first decoder block it would be the output of the bridge. So like this it goes. So here the skip connection would be s3, and we would reduce the number of feature channels by 2. It would be 256. So we're going to copy this again. It would be d3. Okay, and the input would be d2. Skip connection would be s2, and it would be 128. So now the last decoder block, it would be d4, and input would be d3, connection d1, and here it would be 64. I hope you are getting what I'm doing. If you have any query, you can please comment below. And if you have reached till now, till this part of the video, then I hope that you enjoyed it, and if you like it and want more videos like this, so please subscribe the channel and press that bell icon also, so that you get my future videos also. Okay, now let's continue with it. So let's print its shape. So I assume that the shape of d4 would be 512 by 512 by 64. Let's print that and check. Okay, so you can see the shape is same, 512 by 512 by 64. So now comes your number of output channels. Like in case of binary segmentation, you need one channel. Okay, and the output activation function would be sigmoid. So here would be output. So outputs, okay, spelling mistake, would be like a 1 by 1 convolution of the number of channel. For binary segmentation, class would be 1, so number of feature channel would be 1, and it is a 1 by 1 convolution, and padding is going to be same, and the activation is going to be sigmoid. okay, and input would be d4. So we're going to build the model. Let's say now we have the inputs very in line number 29 and output in line 49. The mode would be model class, giving it inputs, outputs, and we can also give it a name, say VGG16 UNET. Okay, now we can return the model. Okay, so this is for binary segmentation. So this now if you have like multi-class segmentation, so number of channel would differ. Okay, output, let's say, let's write here binary segmentation. So if your output is multi-class, then the number of channel would depend upon how many classes you want to segment. Let's say you want to segment 5 classes. Okay, so number of feature channel would be 5, and output activation function would be softmax. Okay, and like this your loss function would also change, but we are not going to that part here. We are going only for the implementation. In the next video we will see how to train this. Okay, for multi-class segmentation. Okay, let me comment this part. So your architecture is complete. Now what we can do, we can print its summary to see what is there in the model. Is there any issue or anything is there, we can see. Okay, so you can see we have the output as 512 by 512 by 1. Now if I change the output layer to a multi-class segmentation, okay, so we can see the changes. Now the number of feature channel are 5 instead of 1, because in this 1 by 1 convolution we have 5 classes instead of 1. Okay, so we can switch to the binary, and you can see also see the number of parameters. So this is the implementation of a VGG UNET. Oh no, it's implementation of VGG16 UNET in TensorFlow using Keras API. So I hope I made this concept clearer to you, and try to use this network for any segmentation task. And if you have written the code, then please comment your GitHub code. I will check it out, and I'm gonna post it video about it if you want. So I hope it is clear to you. If you still have any query or any question or want to ask anything, please comment below or message me on my social media. You can also follow me on Twitter, Instagram, and everywhere if you want. Now thank you, have a nice day.